to go over some problems where we look at changing circuits from the time domain into the Laplace domain. And the first thing I want to look at is equivalent impedances. So this is just a circuit with no sources, no initial conditions, just a configuration of impedances. 62.5 millifarad capacitor, 4 ohm resistor, 1 Henry inductor, sorry that looks kind of like my resistor, and a 4 ohm resistor out here. So recall that inductors and capacitors, when transformed to the Laplace domain, inductors go to SL, L, and capacitors go to 1 over SC. So the 62.5 millifarad is going to go to 1 over S times 62.5. And when you do that, that ends up being 16 over S. And then the 1 Henry goes to SL, which just goes to S. So transforming the circuit to one with impedances, I'll have 16 over S here, S, and 4 ohms. So looking in here. So first I'll have 4 in parallel with S, which is 4S over 4 plus S. So that would be this combination. And then that's going to be in series with 16 over S. So finding a common denominator, looks like this. And when I do some simplification, in the numerator that'll be 4S squared plus 16S plus 64 over S times S plus 4. And then to get the final value of the impedance, so what I have now is I have 4 ohms, and then I have this impedance here that I just calculated. Okay, so now to get the final result, I take 4 in parallel with Z, which will be 4Z over 4 plus Z. And if I want to do some substituting, that's going to be 4 plus 4S squared plus 16S plus 64 over S plus 4. All over, 4 times in the numerator, all over 4 plus that in the denominator. So multiplying through by S times S plus 4 in the numerator gives me 4 times following, and then in the denominator I'll get 4 times S plus 4 plus the same quantity. Okay, so I can factor out a 4 from everything, and then I can factor out an additional 4 from the numerator, but I don't have to. I get 4S squared plus 16S plus 64, and then in the denominator 4S squared plus 16S plus 4S squared plus another 16S plus 64. So I can factor out, it looks like another 4 from everywhere. So I'll get s squared plus 16s plus 64. And here I can actually factor out an 8 from everything once everything's added up. But let me not do that yet. So I'll get 2s squared. So factoring out a 4 from the denominator. Plus, that would be 4s and 4s, so 8s plus 16. Okay, I think I got that right. That looks right. Okay, s squared plus 16s plus 64. And in the denominator, I want to factor out the 2, because in looking at these impedances and things, you always want your denominator highest power of your denominator. You always want to be 1. Have a coefficient of 1. So when I do that, I get s squared plus 4s plus 8. So assuming I didn't make a math error, something looks a little wonky, but we'll just go with this, assuming I didn't make a math error. The numerator poles, or numerator roots, are, if you look at this, that actually factors into s plus 8 quantity squared. So I have a 0 double root at s equals minus 8. Then in the denominator, s is minus 4 plus or minus the square root of 16 minus 4 times 8 all over 2. So there, that's minus 4 plus or minus the square root of minus 16 over 2, which is minus 2 plus or minus j2. Okay, so my poles are at s equals minus 2 plus j2 and s equals minus 2 minus j2. Okay, so that's finding equivalent impedances and finding the poles and zeros. Okay, now let's look at a problem with a switch. So, new example. So in this problem, I have a before and after condition. So this is a circuit where we're going to substitute some equivalent stuff. So 625 nanofarads, 50 ohms, position Y, 5 kiloohms, and 2.5 Henrys. And what we eventually want is we want this voltage right here. So the switch has been in position for a long time, and then at t equals 0, it moves to position Y. So the first thing we look at is we look at what was the situation for t less than 0. And the reason we're doing this is we want to find in the time domain what the initial conditions were. So for t less than 0, this has been sitting for a very long time. So this capacitor looks like an open. So what we're trying to find is the capacitor voltage here. And I'll go ahead and label it this way, call it V sub C. All right, so if we look here, a very simple circuit. This 3 amps is going to go only through the 50 ohm resistor, which is going to give me 150 volts here. So V sub C is then minus 150. Okay, so now I want to look at the circuit for t greater than 0. Okay, so here's my capacitor, 625 nanofarads. It's got a voltage on it of minus 150. So this is actually right at 0. So this is t equals 0 plus, just as the switch moves. Okay, and then here's my 5K, and here's my 2.5 Henrys. Here's the voltage that I want, and I want that for all time. So the first thing I need to do is I need to transform the circuit to the S domain. And so this is now going to be in the S domain, t greater than 0. So the reason that I specify that the circuit above here is equal to, is what's going on at just at 0 plus, is that this 150 volt initial condition is only valid in the instant after the switch moves, and then current's going to start to flow, and it's all going to be then transient. So we're going to look for t greater than or equal to 0. So the first thing we do is we have to do, there are no sources here, so we don't have to transform any sources. So what we have to do is we have to transform the impedances. So the 2.5 Henry is going to go to 2.5 S, and the 625 nanofarad is going to go to 1 over S times 625 times 10 to the minus 9. So let me run that calculator real quick. Actually, it may not be that quick. Here we go. Here's my calculator. So 625, 1 over x, oops, sorry, 625, not 652, 625, 1 over x. So that is going to be 16 and 3 zeros. No, 16 and 5 zeros. It seems like an awfully big number. So let's see. 1, 2, 3, 4. Yeah, so it's 1.6 times 10 to the 6th over S. Make sure I didn't do anything weird. Yeah, that's 2.5 Henrys. Okay, just seems like a lot of big numbers. All right, so now let's start making our substitutions for it. So for our capacitor, we got 1.6 times 10 to the 6th over S. That's our 1 over SC. And then we've got to have the voltage source in series with the same polarity as what was labeled in the figure, but remember it was negative because of what it was connected to. And that's also going to be over S because it's modeled as a step function voltage source. Then we have our 5,000, our resistor, and 2.5 S. So now what I can do is to find this voltage. You know, there's a number of ways to approach that. I can write a simple loop equation and then find the voltage by finding the current and taking that times the impedance. So that's probably what I'm going to do. So minus 150 over S plus, so let's define some current I of S, and now this voltage of course became a function V naught of S, and technically I should capitalize that V. So a single loop gives me negative the voltage source because it's a rise, and then I got 1.6 times 10 to the 6th over S times I plus 5,000 I plus 2.5 S I is 0. So some rearranging and collecting of like terms. So I I times, let's see, 2.5 S plus 5,000 plus 1.6 times 10 to the 6th over S is 150 over S. And let's see, it was a double negative here, so when I move it over, it's going to go negative again. Okay, so I is minus 150 over S times 1 over 2.5S plus 5,000 plus 1.6 times 10 to the 4th over S. And multiplying through these denominator terms, minus 150, 2.5 S squared, 5,000 S, 1.6 times 10 to the, I'm sorry, that should be a 6, 10 to the 6th. Okay, and then V is I times Z, so it's going to be this fraction times the impedance, which is 2.5S. So I'll get minus 150 times 2.5S over 2.5S squared plus 5,000 S plus 1.6 times 10 to the 6th. Okay, now I'm going to cancel out the 2.5s because remember, in my denominator, I always want this highest order term to have a coefficient of 1. So I get minus 150S over S squared plus 2,000 S, and then 1.6 divided by 2.5 is 0.64. Okay, so that's my voltage in the S domain. So if I want to find my voltage in the time domain, I just take the inverse transform of that. I'm going to leave this one for you to do because that's easily done on MATLAB, or you can use quadratic formula and factor that denominator and do partial fraction expansion. Either way. But that's fairly easily done to take that inverse transform. My goal here is to illustrate on the circuits how to actually put the circuits into the Laplace domain and do the substitution for the time varying elements. Okay, so now let's look at another example. So this is example 3. Okay, so here I have a voltage source, DC voltage source. I have a 125 nanofarad capacitor that is initially shorted, and then a switch opens at t equals 0, and then a 4K resistor and a 0.5 Henry inductor. And what I'm being asked for is the current and the voltage as shown in the figure. So same exact procedure. We want to look at the circuit for t less than 0. Now in the case where t is less than 0 and the circuit's been sitting for a long time, I have 20 volts. And once again, remember, for less than 0, I'm looking in the time domain because the Laplace domain does not exist. The capacitor has been shorted because that switch is closed, and the inductor also looks like a short. Okay, so what does this tell us? This tells us I sub 0 at t less than 0 is basically 20 divided by 4k, or 4,000. So that's going to be the initial condition on the inductor current. I 0 at 0 is whatever that is, 0.005. 5 times 10 minus third. Yeah, I think that's right. Make sure. 20 divided by 4,000. Yes. Okay, and that's amps. Okay, now the other thing we need is we need the initial condition on the voltage, or on the capacitor. So we need the initial voltage on the capacitor. Well, that is going to be 0 because the capacitor was initially shorted. Was shorted before the switch. Before the switch opened. Okay, so now we've got our situation for t less than 0, which gives us the initial condition. So I sub naught for the inductor at 0 was 0.005 amps. V of the capacitor at 0 was 0. So that's relevant when I redraw my circuit in the Laplace domain. So now let's redraw my circuit in the Laplace domain. So this is the t greater than 0 circuit in the Laplace domain. So the switch is open, so I can eliminate that branch above the 125 nanofarad capacitor because it's not in the circuit because it's open now. Because this is for t greater than 0, my 20 volt voltage source is, for all practical purposes, a step. So the 20 volts goes to 20 over S. And remember, it stays in the problem. I then have my capacitor, which is going to be replaced with a capacitive impedance, 1 over S times 625 nanofarads. So I'll just put a 10 to the minus 9 here. That's my capacitor. And I don't have a voltage source that represents the initial conditions on the capacitor because the initial conditions are 0. And then here's my resistor, it's 4,000. And here is my inductor, which is going to go to SL, but we're going to have a current source in parallel with that. Now our current was defined in this direction. So this is I naught of S, which means that my initial condition current source is going to be pointed down, and it's going to have the value of the initial condition on the current, 0.005 over S. And my inductor is 0.5 S. Okay, and the voltage that I want is this voltage across the inductor. So in this case, and let me be clear, it's the voltage between these two nodes. In this case, it might actually be easier to write that as an inductor in series, or as an inductive impedance in series with a voltage source. I'm just going to put 1 over SC so I don't have to write all those numbers here. Here's my 4,000. Okay, here's my I naught of S. And here's my 0.5 S. And I could put that using source transformation. I could do that as an inductor in series with a voltage source. And so this voltage source using the source transformation is I times z, so it's 0.5 s times 0.005 over s, and so the s's will cancel. That source voltage will be 0.0025 volts. Okay, so now everything is a series circuit, and I can solve for I naught of s by doing the same thing I did previously. I naught of s, writing a single mesh equation, doing a significant amount of algebraic simplification. Now here's what I want to talk about, because this is where this whole inductor in series with a voltage source gets a little interesting. So let's come back to our initial circuit. Let's use a different color. Notice that the voltage that was asked for was the terminal pair across the inductor in the time domain. So if we come down here, that's the same terminal pair that I'm overriding here in blue. When we did our source transformation to make it easier to solve our circuit, we substituted between the blue dot terminals. Those become these two terminals. So if you use a source transformation to make this an easier problem to solve as far as finding the current I naught, then when you get to where you calculate the voltage across that inductor, in this figure, that is the voltage between these two terminals. So you're going to have both the voltage drop here across the inductance, which is I naught over, or which is 0.5 s times I0, and then you're going to have to include this series excuse me, this series voltage source. So best to do that in the S domain, because everything is a function of s, and then transform back to the time domain, because you can do, it's just going to be easier to do. So that's kind of the way, and let me just re-emphasize what I just said. So your whole V naught of s, it is this entire voltage between these two nodes. So what you need to do is you need to solve for I naught of s, okay? And for the moment, leave it in the S domain. And then you can do one of two things. You can either come back to this figure, and you can write like, you can put a ground here, and you can write a single node equation right here. Current into the node here is known because you just calculated it. This current source is known. So it's really easy if you label this node voltage Vs, it's really easy to write a node equation right here. In fact, I can even write it for you. V of s, referring once again to this node with a ground placed at the bottom node, Vs, okay, the node equation there is going to be minus I0 of s, which you've already solved for, plus V0 of s over 0.5s, that's the inductive impedance, plus 0.005 over s. So I would do the source transformation and use this circuit at the bottom to solve for I naught of s, and then I would go to the circuit above it and write a node equation to solve for V of s once you have I naught of s. This will allow you to solve for V naught of s, and then you can take the inverse transform of it, and you can also take the inverse transform of I. Now what you should expect to get is there will be some differences, but you should get the same basic functional form. So in other words, if V naught of s is a damped exponential, I naught of s should have that in it as well. It won't be exactly the same, but it'll be the same kind of basic family of functions, which is why I made such a big deal earlier on about learning how to do that, learning how to just kind of know what your final result should look like. All right, I think I just want to work one more example, and I don't think I'll work this all the way through. The biggest problem I've seen students have is not in once they sort of have the stuff figured out. The problem I see students having is in finding the initial conditions. So this is problem 13. The figure number is 1315. The problem number is also 1315. So the basic circuit. This is another one with a switch. And like I said, I want to set this one up for you and show you what the circuit looks like, but I don't want to solve it all the way. I'll let you do that. Okay, that's a short. And then I have 80 ohms, 8 ohms, 20 ohms, 6.25 microfarads, inductor, 6.4 millihenries, and what we're interested in finding is V out of T and IL of T. Okay, and the switch was initially here at position A, and at T equals 0, it switches to position B. So first, let's analyze the circuit before the switch moves. So in that case, we have 9 amps, 8 ohms. The switch being in position A puts the 8 ohms and the 80 ohms in parallel, and 20 ohms, and my capacitor is an open, and my inductor is a short. So what I want to calculate is, here was my inductor. I want this IL of 0 for my initial condition on the inductor, and I want the voltage across the 20 ohm resistor. So now if you look carefully, you see that basically the 20 ohm and the 80 ohm and the 8 ohm are all in parallel. So let's combine the 8 and the 80 so that we can use a current divider. So 8 in parallel with 80 is 640 divided by 88. So let me get you a number for that. Keep losing my calculator button on my calculator over here. So 640 divided by 88 is 7.27. Okay, so now I have a current divider. If I want the current both through the 20 ohm resistor as well as IL of 0, so IL of 0 is the resistor that I don't want, 7.27, over the sum 7.27 and 20. Okay, so let me just kind of show you. Okay, here's the 9 amps. Here's the 7.27, and here's my 20 ohms. And I want this voltage and this current. Okay, so I take this current divider ratio, so I'm calculating the current through the 20 ohm resistor. I take the current divider ratio and I multiply it by the total current. So let's work that out real quick. Divided by 27.27 equals times 9. I'm getting 2.4. 2.4 amps, and that makes sense. It would be, given the ratio of the resistors, it would be less than half. Okay, now that I have IL of 0, I can calculate the initial condition on the capacitor. That's going to be 2.4 amps times 20 ohms, which is roughly 48 volts. Alright, so that little calculation gave me the initial conditions. So now what I need to do is I need to sketch the circuit after the switch moves. So after the switch moves, the current source and the 8 ohm resistor are removed from the problem. And I'm going to have a short circuit in parallel with the 80 ohm resistor. So let's look up here at my circuit. When the switch moves, I've got a short in parallel with the 80 ohms. So the 80 ohms is going to be shorted. So what my circuit's going to look like after the switch moves for t greater than 0 is I have a short for everything 80 ohms and left. This 20 ohm resistor is in place. The capacitor is going to be, I'm going to give myself enough room here. The capacitor is going to be 1 over, and if you'll pardon me, I'm just going to write this as 1 over SC, just for purposes of trying to keep the notes neat. C is 6.25 times 10 to the minus 6, so you'd substitute that in there to get a number. And then that's going to be in series with a voltage, and the voltage that we defined with polarity from left to right, okay, because of the direction the current was defined. So that voltage source is going to be like this, and that's going to be this 48 over S. Okay, and then over here on the inductor, got my inductor. It's going to be, where'd my inductor go? S times 6.4 times 10 to the minus 3. That's my inductor impedance. And then in parallel with that, I've got a current source with the same direction as the current calculated for the initial condition, and that's going to be 2.4 over S amps. Okay, so that's what your circuit looks like. Now, what do you actually want to know? You want to know, let's track back up here, we want to know the voltage across the capacitor as a function of time. So let me come here and identify really clearly where we want the voltage. We want the voltage right here. Now, in your original circuit, the 6.25 microfarad capacitor was in parallel with the 20 ohm resistor. Oh wait, I'm sorry, you don't want that voltage. You want the voltage across the inductor. Well, never mind then. So let's use a different color. Let's use pink for what we actually want. So we want the voltage across the inductor. So that's this voltage, V out of S. And then we want the current in the inductor. So if we come back to the original problem, here was the current. Okay, that current's also flowing in this branch here. So the current we want is right here. Okay, we cannot, so what can't we do? I'm running out of colors here. Green is bad, okay? We can't calculate this current and call that the inductor current, because the equivalent that we substituted, it's actually the current in the inductor, in the inductive impedance, and the current source represented by the equivalent Laplace representation of the inductor. So the actual inductor current is the sum of both of those. So it's going to be, it could be represented as the current in this branch. So if you look here, once again at the original circuit, here was that current, came through the inductor, came here. The difference in our equivalent is that we have a parallel substitution that we made for that inductor. So the easiest thing to do is just solve for the current in this branch. How would you do that? You know, it just kind of depends. If you look carefully at this, this is an all parallel circuit with the exception of these two items here. So you could reconstruct this and show this as the 20 ohms and this current source all being in parallel. You could do a source transformation here. I'm going to leave you to play with that and work with that. Obviously, this is kind of a lengthy problem. As far as the problem goes, this is not necessarily the type I would ask you to solve all the way out on an exam. But what I would be very interested in is, can you generate this equivalent circuit representation? So that's part of what I would be interested in testing over. But for the homework, it's very good practice to try and work this all the way through and get an actual result. Okay, I think that's all that I want to work out as far as examples on how to transform circuits into the Laplace domain. We've had some good examples here of how voltage sources are transformed, how we track through the variables in the equivalent circuit to be sure that the answer we're giving is actually the question that was being asked in the time domain circuit. We saw that on a couple of these circuits. So I think I'm happy with kind of showing you these examples, because this is the main thing that I want you to get out of the course as far as the solving of circuits with Laplace. You can get this very complicated. You can have multiple loop circuits, have to write mesh equations or node voltage equations with unknowns. It's solved the same way a circuit is solved, except it's an algebraic expression, not a constant like you would solve in a DC circuit. So I don't actually go over that much in the class or test for that much in the class, just because it's kind of a rehash of circuits 1, because it's examples and testing on the mesh current method and the node voltage method. So, so this is the extent of what I want to illustrate, at least in this lecture, on solving circuits using Laplace.